So like I said, last week we dealt a lot with the disk method. This week, we're gonna move on to the shell method, okay? I know I kind of motivated this last class period and said, well, the reason we want another method is because sometimes it's really hard to solve for one variable or the other. So if I have an equation that's hard to solve for y, I hope that I can have a method where I can integrate with respect to x. Well, the shell method is another method. It's also an easy method to deal with when we have figures of wholes as well, right? So let's talk briefly about the shell method. So we're still going to be measuring volume of an object rotated around either a horizontal or a vertical line. So we're going to be in the same scenario as last week. We're going to have some area in 2 dimensions, and we're going to say create a 3-dimensional object by rotating that around horizontal line or rotating it around a vertical line. But instead of using disks and washers, we're going to use nested shells. I'll talk about what I mean by that. All right. When I say a nested shell, I'm talking about essentially a cylinder with a hole cut out. Enable the editing there. Oh, wait. No, edit. Huh. Doesn't allow me to edit that, but it should say with hole cut out. Okay. So it's basically, think of it as a pipe or a straw or a tube. Okay. And the volume of that pipe is going to be, or straw or tube is going to be 2 pi times the average radius times the height times the thickness. 2 pi radius, height, thickness. And then we're going to nest these shells inside of each other. And we're going to let the thickness of those shells get smaller and smaller and smaller. Limit as the thickness goes to 0. And then that's going to turn into our integration. All right? That's the big idea. So let me draw a picture. Let's say we just have an area, I don't know what. From A to B, and we rotate that around the x-axis. So my area is right there. And I rotate that around. So I have this ghost area. Something like that. Okay. So we're rotating this area around. And what we're going to do is we're going to create nested shells. So instead of taking a rectangle in the disk method way, I take a rectangle in the other way. Yeah. Now, this is probably a bad example because the rectangles up here are gonna be messy. But if I rotate that rectangle, what I've done is I've created essentially a little pipe or a little shell. Just like that. Okay. And the volume of a shell is 2 pi. When we say radius, we're talking about the radius here. Radius of a cylinder. The height is how long that cylinder is. And then how thick this shell is. All right. That's the volume of one shell. What we're going to do is we're going to let the thickness get thinner and thinner and thinner and thinner. And as that thickness gets thinner and thinner and thinner and thinner, we're going to sum up lots and lots of shells and let the thickness get thinner and thinner and thinner. And the total volume of the object is going to be 2 pi integrate the radius. The radius we actually call rho of x so that I don't confuse it with the radius from the disk method. So we got a new letter. So we use rho, the Greek letter for r. Height is h of x integrated with respect to x from a to b. Now, is that what this is? No, this is not the way I drew this picture, right? That picture that I just drew, where we revolve around the x-axis, notice the thickness is a measurement of change of y's. Does that make sense? So for the shell method, this one we use with a vertical axis of revolution. That's using the x. And we use this one, the one with the y, with horizontal axis of revolution. right? So those are my formulas for the shell method. So the shell method formulas you see right here. Horizontal axis of revolution, now you're integrating with respect to y. Vertical axis of revolution, now you're integrating with respect to x. That was exactly the reverse from the disk method. All right. And hopefully you noticed in the picture that I had drawn, it had to be that way because in the disk method, I would have drawn my Riemann sum rectangles vertically in the picture I had on the board. Whereas in the shell method, I have to draw my Riemann sum rectangles horizontally. So disk method, I have to draw the rectangles one way. Shell method, I draw the rectangles perpendicular to that. And so horizontal axis, now we integrate with respect to y. Vertical axis, now we integrate with respect to x. Okay, so let's do an example of how this could work. So we want to find the volume using the shell method. Of the region created by y equals 4 minus x squared, x equals 0, and y equals 0 in the first quadrant. And that region is going to be revolved around the y-axis. And we'll use the shell method to do this. So let me draw that region. Now we've seen this region before. In fact, if you look back, we've actually seen this problem before. So we have this region. And we want to revolve it around the y-axis. Now, obviously, the y-axis is vertical. So we're going to use the value with respect to x. What the shell method says to do is take a rectangle, a representative rectangle, not just a rectangle, but there'd be infinitely many, right? We're going to take Riemann rectangles, oriented that way. And when you spin that around the y-axis, you get shells. I'm gonna draw a cylinder. That, again, look like pipes or cylinders or whatever, right? But the important thing is we have to integrate with respect to x because that's how our Riemann sum rectangles are going to look like. So let's take 2 pi, integrate from A to B. The radius, which we call rho, times the height, which we call h of x, dx. Now, here's the deal. If you think about what the radius of this cylinder is, notice that we're measuring from the middle of the tube to where our edge of the tube is, right? So we're measuring, once again, from the line we're rotating around all the way to our rectangle. Now, where is our rectangle at? Well, this one might be somewhere. It's just at all of these different places, isn't it? We're going to have all of these rectangles. Does that make sense? I only drew one just to kind of show it off, what we're doing, but there's going to be infinitely many rectangles as we take the limit of the thickness going to 0. Technically, this rectangle is at an arbitrary x value in the region, within the region. So we're going from an arbitrary x value down to x equals 0. Does that make sense? So my radius in the shell method is just that. It's arbitrary x value down to 0. Now the height of this shell is going to be the top to the bottom of this rectangle that I just drew. And any other rectangle, right? There's going to be many, many rectangles in there with the Riemann sum. So top of this rectangle is determined by the curve y equals 4 minus x squared. So the top of the rectangle is 4 minus x squared. The bottom of the rectangle is y equals 0. And just like we have before, since we're integrating with respect to x, we're going to look at the left-hand x values of the region. Over to the right-hand x values of the region. So since these are x values, we're going from x value of 0 all the way to an x value of 2. So we're going to be integrating from 0 to 2. So the key thing there is radius is arbitrary x value down to the line we're rotating around. Height is top of the rectangle to the bottom of the rectangle. After we get this, we can plug it into our calculator Make sure you put parentheses in the right spot and all of that. And what you end up with is about 25.13 or 8 pi. Now, if you go back to our 7.2 material, this was actually one of the problems in 7.2. And when we did this in 7.2, we got the exact same answer. We got 8 pi when we did that problem in 7.2. Wasn't our first example, but it was one of the first few examples in 7.2. So we see that we get the same volume either way. So this confirms that both methods are giving us the same thing when I can apply both methods. The advantage to this method, as opposed to what we did last time, is that in this method, I didn't have to solve for x. If I did this using the disk method, then I'd have to solve this equation for x, and then I'd integrate with respect to my y values. So it'd look a little bit different, obviously, but turns out you get the same answer. Does that make sense? So again, radius is arbitrary value down to the line we're rotating around. Arbitrary x value in this case. And then our height is top of the rectangle to the bottom of the rectangle. We integrate left hand, in this case, left-hand side of our region over to the right-hand side of our region, since we're integrating with respect to x. Okay. So we see that in the shell method, we can do all the same stuff that we've done in the disk method. In example 2, we're going to take the same region we just dealt with, but instead of rotating it around the y-axis, we're going to rotate it around the line x equals -3. If we were using the disk method on this, it would be fairly cumbersome. What would we have had to have done if we use the disk method? Well, I would have had put my rectangles horizontally, and then they'd rotate all around. And obviously there's a hole inside here, so it's a washer method with the disk method. So it's a washer method if I did that. Here's one of the nice things about the shell method. The shell method handles holes very nicely. Now, x equals -3 is still a vertical line. So we're going to utilize x values with the shell method. We're going to integrate with respect to x. Since x equals 3 is a vertical line, x equals -3, excuse me, is a vertical line. Now, if I draw an arbitrary Riemann sum rectangle, like I did already, so I'll just leave the drawing up there. So I draw a Riemann sum rectangle. There's going to be lots and lots and lots of those in that area, but I just drew one representative one. It's going to be at some arbitrary x value. And the radius is going to be from that arbitrary x value all the way down to the line x equals -3. So the radius now goes from arbitrary x value down to -3. Is that okay? Arbitrary x value down. The height of this Riemann sum rectangle, well, it's still going to be top of the rectangle to bottom of the rectangle. Top of the rectangle is 4 minus x squared. Bottom of the rectangle is 0. What should my integration be to and from? Well, we're still going to just integrate this green area, this shaded green area. So my integration is still from 0 to 2. I've just changed my radius. So it's still from 0 to 2. Notice if we start at 0, we avoid any possible shells on this side, right? And so what we've done is we've done a shell method where essentially we have these nested shells and it just stops with a hole in it already. Does that make sense? So we have, I don't want to draw it too big, but think of it as we got a bunch of nested shells. All inside of each other. And at some point, we just stop and leave the hole in. Right? Because there's a hole in this thing. So with the shell method, we just take a bunch of nested shells, and once we get to the inner edge here, we stop. We start at the inner, end at the outer, or vice versa, however you want to think of it. And we just stop. If you wanted to clean this up a little bit before you throw it in your calculator, radius becomes x plus 3 height becomes 4 minus x squared. And that's usually how I throw it in the calculator. Notice this is very, very similar to what we did in the previous problem, obviously with just a different radius. And I got essentially 40 pi. Which is approximately 125.66. Is that right? So rotating this region around the line x equals -3, as opposed to rotating around x equals 0, is not really any bigger of a task. I just have to adjust my radius, and then we're all set. By the way, does it make sense that this value is larger than my previous example? My previous example, I rotated around the x-axis. This one, I rotated around x equals -3. So the radius got a lot bigger. It's like saying, if you have a tube and it goes in a circle, and it's a really small circle, and then you have a tube that goes into a bigger circle. Well, it's not even a circle, but you guys get what I'm saying. Which one of those are you going to need more tubing for? Pretty obvious, right? The bigger one. That's what we just said. This little region rotated around the x-axis is basically going to be like a really small rotation. As you get a bigger rotation, you're going to need more volume of stuff. I'm sure we've all handled Play-Doh as a kid, made a little tube, right? Well, if you made a gigantic tube of the same thickness, you need more Play-Doh, right? That's the principle that we're getting at. And the only way to make the tube bigger, well, there's two ways. One is to make your thickness smaller. We didn't do that. It's the same size thickness every time. This area is the same size thickness every time. So you can make your thickness smaller, or you can add more Play-Doh, right? That's general principle. All right. So that's this example. Rotate around vertical lines. You can see that in these first two examples. Now let's rotate around a horizontal line. In particular, let's take this same region that we've dealt with in the first two examples, and let's rotate it around the x-axis. So we've drawn that region a few times already. The one bounded by 4 minus x squared, x equals 0, and y equals 0 in the first quadrant. And we're rotating it around the x-axis. Now we're going to use the shell method. So we're going to be integrating with respect to y when I rotate around horizontal lines. And the reason I have to do that is because the typical Riemann sum rectangle on the shell method is going to be parallel to the line I'm rotating around. Okay. And so I'm creating shells that essentially look like little cylinders, something like that, right? This to that. Just like we had before. Oh, I'll do this. The radius in the shell method is going to be from some arbitrary height down to the line I'm rotating around. So radius in the shell method, again, that symbol there is rho. I don't say that a whole lot. I use radius more than rho, but rho means radius. So it's an arbitrary y value down to y equals 0 because I'm rotating around the x-axis. The x-axis is y equals 0. So arbitrary y value down to 0. Height of the rectangle. Well, the height of the rectangle, or the height of the cylinder, is the length of the rectangle, or height of the rectangle, doesn't matter. Height of the cylinder, height of the rectangle, interchangeable. That is going to cause me to have to solve this equation with respect to x. I need x equals. So if you remember what we did last time, we added x squared to both sides and then subtracted y from both sides, and then said because we're in the first quadrant, we can take a square root of 4 minus y, and I can take in particular the positive square root of 4 minus y. So that's the right-hand side of this rectangle, given by that. So the right-hand side of my rectangle is given by this. The left-hand side of my rectangle is simply x equals 0. It's my y-axis. So right-hand side is always this curve. Left-hand side is always x equals 0. And so I go from the top of the rectangle, square root of 4 minus y, down to 0, integrate with respect to y, from where to where? Do I know what bounds I gotta use? Well, they have to be y values. So the bottom y value is y value of 0. Top y value is y value of 4. So my bounds have to go from 0 to 4. Yeah. We've plugged that into our stuff like that, I should say, into our calculator enough that, you know, it doesn't matter which variable You can use y's by just doing alpha y. You could use thetas, you could use whatever you want. And what you get is essentially 17 and 1/15 times pi, or roughly 53.62. By the way, when I solve that, I know it's 17 and 1/15 times pi. For two reasons. One reason is we did it last time, so it should have been 1/15. But also, if you look on your calculator, it isn't exactly 17 and 1/15. Because we are using the square root, because I'm using this square root, you get 17.0666, and then it's off by a few decimals. That makes sense? Because of the way the calculator does the computations, it kind of throws your answer off by just a little bit. Does that work? But I know it's 17 and 1/15. By the way, we did this example using the disk method. All right. And when we did the disk method, we integrated with respect to x because the rectangles would have been this way, and then you ended up with disks. And once again, we got the same answer using the disk method as there. All right, so let's take a new region. We're going to take the region created by y equals 5 minus x. Y equals 0. X equals 0. And y equals 4. And we're going to revolve that around the x equals 5 line. And we'll do this with the shell method. Now, this is a kind of a unique region, because if I'm doing this via the shell method, in one section of this, I'm going to have my Riemann sum rectangles go from y equals 4 down to y equals 0. Anybody see that? In another section, my Riemann sum rectangles are not going to go from y equals 4 down to y equals 0. They're going to go from y equals 5 minus x down to 0. Okay. So because I have two different tops to my rectangles, I'm going to have to create two different integrations. So I need to create two different integrations. Now, there's actually a couple of different ways you can see this. Some people would say, let's create two different area sections. One area is here. Now, let me just say, let's draw some points here. That's the origin. This is the point 1, 0. This is the point 1, 4. This is the point 5, 0. Does that make sense? And this is, by the way, the point 0.05. Okay. So option 1 is to create two different regions and add those up. How many other colors? You can see one of the regions right there. Okay. And if I did shell method, on that region, it would be 2 pi. I'm integrating, well, first off, everything's with x values. I should have said that. This is x values. So let me write rho of x, h of x, x from a to b, plus 2 pi. I guess this would be, I'll call it A1, B1, and this is A2, B2. Another different row of x. I guess this is my second radius, second height, first radius, first height. Is that okay? Subscripts. I'm gonna do region 1 area, or excuse me, not region 1 area, region 1 value plus region 2 value. Okay, and I can use subscripts, or if you don't want to use subscripts, just know in your mind those are different A's and B's, right? So this first region, the one I've highlighted here, we're going to go from an we're gonna go from 0 to 1 in the first region. 0 to 1, that rectangle. My radius is arbitrary x value down to the line I rotate around. So I'm rotating around x equals 5. So it's x to 5. Now, here's another trick. Here it is kind of important which one you write first. Notice the 5 is the bigger than whatever these x values are going to be. So if you want a positive radius, you say, let's actually start at 5 and go down to x. That gives you a positive radius. Height of this rectangle. Well, the top of the rectangle is always y equals 4. The bottom of the rectangle is always y equals 0 in this part or in this region. So it's from 4 down to 0. Then I move on to the second region. The second region is this one that I'm highlighting. And there's a rectangle from the Riemann sum. This second region goes from 1 to 5. So we're going to be integrating from 1 to 5. Notice that where we stopped our region over here is where we started this region over here. Again, the Riemann sum rectangle is just going to be at some arbitrary x value. And there's going to be lots of these rectangles, some here, some here, some here, right? So it's still the x value up to 5, or if I want a positive, make sure I start with the bigger one. 5 is bigger than all of these x's. So if I want a positive radius, I make sure it's 5 minus x. Now the top of this rectangle is determined by the line y equals 5 minus x. Top of that rectangle determined by the line 5 minus x. And the bottom of the rectangle is y equals 0. And so that big long thing is how I calculate the total value. So the volume of this plus this. Rotate around x equals 5. So total value of the region, rotate around x equals 5. I've not calculated that yet, so let me type that in. And what you end up with is about 78 2/3 pi. Or in other words, about 247.14. Now, like I said, that's just option one, is we create two different sections and then add them up. Anybody know, well, anybody have any insight on what option two would be? Any thoughts? First of all, is everybody okay with option one, or understand how I got it? Okay. Well, option two is actually subtracting a volume from another. Or one region minus another. Okay. And basically what you do, I'm gonna try to highlight this the best I can. Is you would say, well, here is a big rectangle. The red and green together. Or not red, I said rectangle, sorry. Big triangle, the red and green together. Here. Right? Big triangle minus, and then I take out the red triangle. Everybody follow that? So the big triangle, subtract out that small red triangle. That will give me the area that I'm looking for in the green, not the area, the volume. The volume created by taking this area, rotate around x equals 5. Okay. And so that's basically it. Let's see if we get the same thing that way. All right, so we do the big triangle minus small triangle. Rotated around, obviously. So I'm talking about the region that I'm rotating there. All right, so let's talk about the big triangle. Big triangle goes from 0 all the way to 5. No matter where you're at in the big triangle, the top of the big triangle is always y equals 5 minus x. The bottom of the triangle is always going to be y equals 0. So that's giving me my height. My radius is still just arbitrary x value to the line I'm rotating around. So my radius is still 5 minus x. My height is top of the rectangle down to bottom of the rectangle. 5 minus x minus 0. And then the small rectangle. Well, the small rectangle, I keep saying rectangle for some reason. Small triangle. Oh, I keep saying rectangle. Sorry. Small triangle. Small triangle is this little red one. I'm going to be integrating from 0 to 1 there. My radius, again, I'm at some arbitrary x value, wherever I'm at there. And rotating around x equals 5. So as long as I want a positive radius, I want to make that a 5 minus x. Top of this Riemann sum rectangle is 5 minus x. The bottom of that Riemann sum rectangle is y equals 4. So top of the rectangle, 5 minus x. Bottom of the rectangle, 4. And by rectangle, I mean this Riemann sum rectangle. Okay. And if we type that in, hopefully we get the exact same number. Let's see that I do. In fact, let me throw it on my calculator. So you can see the previous typing in the previous one, 2 pi integration plus 2 pi integration. That was what I had earlier. Now this one is going to be 2 pi integrate from 0 to 5. My radius is 5 minus x. And my height is also 5 minus x. Could have just squared that, I guess. But that's the big triangle rotated around. And then the small triangle is going to go from 0 to 1. Radius is, again, 5 minus x. Line I'm rotating around down to arbitrary x value. And the height is going to be 5 minus x down to 4. Make sure I have all the parentheses in the correct spots. Looks like I do. Hit enter. Sure enough, we get the exact same number, right? $78 2/3 times pi. Any questions about that? So sometimes when you have these sort of complicated regions, you can split this up into different ways. You can split it up into parts and add up all the individual parts. Or sometimes you can see it as one big thing minus a smaller thing. Either way is fine. Either way gives you the exact same answers. So it's just a matter of preference of how you like to see it. Okay. So I want you to do this example 5. I want you to try this on your own using the shell method. Find the volume created by revolving this region around the line x equals 2. All right. So on this one, the region that we're looking at has, it's almost triangular shape. This one curve, y equals x to the third plus x plus 1, is not quite a straight line. I can't even remember if it dives in or out a little bit more in that section. But we get this region, this near triangular region. Okay? And the 3 points of intersection are 0, 1, 1, 1, and 1, 3. Now we're revolving around a vertical line. So with the shell method, our Riemann rectangles are going to be parallel to the line we're rotating around. And so we're integrating with respect to x. This is a nice solid region. All of my Riemann rectangles have tops, which are this curve, bottoms, which are this line. So we're only going to do one integration here. We're going to integrate from x value of 0 to x value of 1. My radius is going to be from some arbitrary x value in this section to the line I'm rotating around. I'm rotating around x equals 2. Now, if I want my radius to be positive, I notice that the 2 is bigger than the x values that I'm going to be plugging in. All of the x values are going to be between 0 and 1, so they're smaller than 2. And so if I want my radius to be positive, I write 2 minus x. What's going to happen if you accidentally write x minus 2? Well, if you accidentally write x minus 2 instead of 2 minus x, the volume comes out as a negative rather than a positive. Okay, so that should just be, volume being negative should be sort of a red flag, and you say, oh, I know what I'm doing. I just flip-flopped my x and my 2. And that's an easy fix. All right, height of this Riemann rectangle, the top of the rectangle is determined by x to the third plus x plus 1, y equals x to the third plus x plus 1. The bottom of this rectangle is determined by y equals 1. So be careful about that. Bottom of the rectangle determined by y equals 1. And then we're going to integrate everything with respect to x. I've already plugged that into my calculator and got, well, you can write this a number of different ways, but 29/15 times pi, or approximately 1.9333 repeating times pi, or approximately 6.07. Since it's in volume and being cubic units, whatever units we're dealing with. All right. Any questions about this? Now, this example really highlights the advantage of having both the disk method and the shell method available to us. If I were to try this same problem using the disk method, I would have had to integrate with respect to y, which causes me to solve this for x. And solving y equals x to the third plus x plus 1 for x is really difficult. Okay, if not impossible in this section. So think about how you'd actually even try to solve that. That'd be a really, really tough thing to do. Solving this for x. So it'd be very, very difficult and quite frankly, not worth the time to do if we had to do it. Okay. So essentially we just don't. We say, well, let's just use the shell method instead. And by the way, like I said, it's not just nice to have the shell method, it's nice to have both methods, because you can imagine if you wanted to rotate this around a horizontal line, this shell method, you'd have to integrate with respect to y, and then you'd be in the same problem spot of solving this for x. That makes sense. So if you rotated this around a horizontal line, you'd want to use the disk method probably, so you don't have to solve this for x. But here we rotate around vertical, so we wanted to use the shell method, so we didn't have to solve for x. Right? And like I said, that's the advantage of having both methods. Sometimes disk method is nicer, sometimes shell method is nicer. Oh, I went the wrong one. There you go. All right, let's do another. So this is a famous math object. I say famous, not super crazy famous, but just well-known object in math called a torus. So a torus is basically like a donut-shaped figure. You take a circle and then you rotate it around. It's like the Play-Doh figure that I was talking about earlier. You have a tube that's connected on both ends. So we're going to take a circle of radius 3. Centered at the origin. So that's our region. The bounded region created by that circle. And we're going to rotate it around the line x equals 6. Again, this thing's called a torus. If you go into higher mathematics, you'll, especially in topology, a torus is a unique figure. All right. All right. Now, we're gonna use the shell method. Again, my region is this entire thing. The entire circle. Again, centered at the origin. And let's label these points so that we're all on the same page. This is the point 0, 3. This is the point 3, 0. This is the point -3, 0. And this is the bottom point 0, -3. We're rotating around the x equals 6. Again, you can imagine this big tube going around in a circle and then connecting back to itself. Right? So it's like one big hula hoop, basically. Right? Big tube goes around in a circle, connects back to itself. Like a hula hoop. Or a donut, or a Play-Doh snake connected at the ends. Right? So like I said, we're going to use the shell method. So the shell method, the rectangles in the Riemann sums are going to look similar to this. The top of that rectangle is going to be at the top of the circle. And it's going all the way down to the bottom of the circle. Because we're using the shell method in this way, the volume of the circle, the volume of the torus created by the circle, we're going to find by integrating with respect to x. Rho of x times h of x dx. Now, most of the fill-ins are fairly straightforward. This region has x values that go from -3 all the way to +3. So -3 all the way to +3. By the way, I have nice whole numbers here, but obviously if it was x squared plus y squared equals, let's say 10, you'd have to go from negative square root of 10 to positive square root of 10. Okay, so you have to have square roots in there too. So -3 to +3. Now let's talk about the radius. Well, wherever this is at, it's at an arbitrary x value, right? Wherever that Riemann rectangle is at, whether it's here, 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 arbitrary x value, and we're rotating around the line x equals 6. So if I want a positive radius, since my region sits to the left of the line I'm rotating around, a positive radius can be found by taking 6 minus x. Now, the last piece is going to be the hardest piece. And that's figuring out the top and bottom of one of these Riemann rectangles, which is the height of the cylinder that we're creating. I need to solve this to get y equals. So the first thing I'm going to do is subtract x squared from both sides. That'll give me y squared equals 9 minus x squared. Now, here's the thing we need to know about circles. If I'm solving for y, if I take a positive square root, what portion of the circle is that? Well, this is a positive y value. So all of the y values which are positive means that's the top of the circle. The positive square root is the top of the circle. And on the other side, if I took a negative square root, that is the bottom of the circle in this instance. So that's the bottom of the circle. So negative square roots give you the bottom of that circle. Positive square roots give you the top of the circle. So the height is going to be from the top of the circle, which we now know as y equals square root of 9 minus x squared, down to the bottom of the circle, which we know is negative square root of 9 minus x squared. Notice that negative of a negative is going to give you a positive, right? And by the way, if I take square root of 9 minus x squared plus another square root of 9 minus x squared, you can rewrite that. So 9 minus x squared plus another 9 minus x squared is 2 9 minus x squareds. So sometimes people, when they write it in their calculator, prefer to write it this way with a coefficient of 2 rather than doing a double square roots. So a second, but I get approximately 1065.92. By the way, if you divide that by pi, you get another ugly number. If you divide that by pi, you get 108. So what this really is, or what it should be, if our calculator calculated it perfectly, is 108 times pi squared. So a torus is an interesting figure because the value involves this pi squared. And one of the pi's is coming from this circle. The other pi is coming from the circle that's moving it around, right? So this cross section is a circle, but also we're moving the whole thing around in a circular motion. So we're moving a circle in a circle. Circle in a circular motion, and that ends up with a pi squared, interestingly enough, in the value. That's not the important thing. The important thing is that we can set it up. Remember, it's always, height is always top of the Riemann rectangle, down to the bottom of the Riemann rectangle. Radius is always arbitrary x value to the line we're rotating around, or arbitrary y value to the line we're rotating around, depending on how we're integrating. And then the bounds are the bounds of the region itself. You could do this using the disk method if you wanted to, but it'd be tough. It'd not be be a tough thing to do. You'd have to create some washers, and then if you're doing disk method, you'd have to do left-hand side of the circle versus the right-hand side of the circle. But you can do it. It's not that big of a deal. So that's the volume of a torus, or that particular torus, I should say. Okay. So that is the last example in 7.3. Hopefully we've done enough shell method examples that we can feel comfortable moving forward using one of these integrations, right? Remember, with the shell method, horizontal axis of revolution, we're integrating with respect to y. Vertical, I'm integrating with respect to x. That is the reverse of the disk method. And that's also why it's nice to have. The next section we're going to do does not deal with value. Okay. We're going to deal with arc length and surface area in 7.4. So we're going to deal with a very different concept of not the volume of an object, but the surface area of that object. And not the area of an object, but the arc length of a curve. And arc length is connected to surface area in a similar way that 7.1, those regions, the area of those regions, were connected to the value. We're going to take an arc length and spin it to create surface area. Right, that's basically the whole thing. So because we're only at 10 minutes left in class, I don't think we need to start 7.4 today. We'll start 7.4 next time. We've had two kind of shorter days in a row, 10 minutes short, but so we'll start this next time. And if you want to, you should be able to do all of the 7.3 homework using the shell method and have that done. So that's due on Friday. We'll finish up, we'll do all of 7.4. My plan is to do all of 7.4 on Thursday, okay? All right, well then I'll see you all next week. Or next time, sorry, not next week.